The envelope detector is an alternative technique for demodulating an amplitude modulated signal. All the commercial amplitude modulated radio receiver utilize this device. It is suited for detecting amplitude modulated signal with a very small frequency range or narrowband amplitude modulated signal. In the narrowband amplitude modulated signal, the carrier frequency Fc is much higher than the bandwidth of the modulating signal. The envelope demodulator is a device that is both simple and highly effective. The output signal produced by the envelope demodulator will follow the envelope of the input amplitude modulated signal. Exactly. Let us see the circuit diagram for the envelope demodulator. The demodulator circuit contains a modulating signal source ST, a diode where amplitude modulated signal ST will be given as an input, and resistor R1 and capacitor C will form a low pass filter. Let us see the block diagram of the operation of the demodulator circuit. At first, amplitude modulated signal is given as the input to the diode. Output of the diode will be passed through a low pass filter, and the low pass filter will provide our desired demodulated signal or message signal. Let us understand how this circuit functions as demodulator. In the circuit diagram, amplitude modulated signal is given as the input to the diode. When the amplitude modulated signal is in the positive half cycle, then amplitude modulated signal or ST is greater than 0 or input to the diode is greater than 0. Then the diode will be in the forward bias condition, or the diode can be replaced by a short circuit. So the capacitor C will start charging towards the peak value of the amplitude modulated signal ST, which is equal to Vm, which is indicated by point A in the graph of the amplitude modulated signal ST. Due to the charging of the capacitor, the voltage across the capacitor increases, and the charging of the capacitor continues until the voltage across the capacitor reaches to the maximum amplitude of the amplitude modulated signal ST or Vm. Finally, capacitor will be fully charged and voltage across the capacitor is equal to Vm. After that, in the positive terminal of the diode, the voltage due to the amplitude modulated signal will be less than Vm, as the amplitude modulated signal ST is less than Vm. But in the negative terminal of the diode, voltage is equal to Vm, same as the capacitor voltage. As the voltage in the negative terminal of the diode is greater than voltage in the positive terminal of the diode will be in the reverse bias condition and can be replaced by an open circuit. So the diode will stop conducting, and so the capacitor will start discharging across the resistor R1. So the voltage across the capacitor will start decreasing from the value Vm. After decreasing for some times, the capacitor voltage will be V1, or voltage at the negative terminal of the diode is equal to V1. And graphically, this voltage at point V is equal to V1. Then amplitude modulated signal ST will increase, and when the amplitude modulated signal ST is greater than the voltage V1, then voltage in the positive terminal of the diode due to the amplitude modulated signal ST will be greater than V1, but voltage in the negative terminal of the diode is equal to V1, same as the capacitor voltage. As the voltage in the positive terminal of the diode is greater than voltage in the negative terminal of the diode will be in the forward bias, so the diode can be replaced by a short circuit, and the diode will start conducting, and due to this, capacitor will start charging. Charging of the capacitor will continue until the voltage across the capacitor reaches to new peak value Vm1, which is indicated by point C. And this process of charging and discharging of the filter capacitor will be repeated. Now let us understand this process from the graphical point of view. Let's take an amplitude modulated signal of the modulation index k less than 1. So the amplitude modulated signal will be an undermodulated signal. We know that the envelope of oscillating signal is a smooth curve connecting its extremes. So the amplitude envelope of this oscillating amplitude modulated signal is a curve that connects the extreme of this amplitude modulated signal. Here, at first, the capacitor will charge up to the voltage Vm1 at point A when the diode is in the forward bias condition. Then the capacitor continues to discharge across the resistor R up to the voltage V1 at the point A prime when the diode is in the reverse bias condition. Again, when the amplitude modulated signal becomes greater than the voltage V1, then the diode will be in the forward bias condition, and the capacitor will start charging up to the value Vm2 at the point B. After that, again the capacitor will discharge across the resistor R up to the voltage V2 at the point B prime when the diode is in the reverse bias. This process will continue as the capacitor charges to the point C and discharges to the point C prime until the capacitor charges to the point E and discharges. So from this figure, it can be summarized that for these durations, the diode is turned on and will be in the forward bias, and the capacitor will charge until the voltage across the capacitor is equal to the peak value of the amplitude modulated signal. And for this duration, the diode is turned off and will be in the reverse bias. The capacitor voltage will discharge across the resistor. So due to this charging and discharging of the capacitor, waveform across the resistor will take the shape like this. These waveforms resembles the envelope of the amplitude modulated signal which we have previously seen. And this envelope of the amplitude modulated signal is the output across the resistor R. If we remove the amplitude modulated signal, then output across the resistor R look like this. By using RC filter, the ripple in the output across the resistor can be removed and the waveform will look like this. To remove the DC component in the output, a DC blocking capacitor can be used. It can be observed from these waveforms that the envelope of the amplitude modulated signal is being obtained successfully, which resembles the modulating signal or the message signal. Here we have assumed that the diode is ideal and the amplitude modulated signal is applied to the input of the demodulator, which is supplied by a source having the internal resistance Rs. Selection of the RC time constant. As we have previously seen, the capacitor charges through the diode and the resistor Rs when the diode is on, and it discharges through the resistor R1 when the diode is off. So when charging, the charging time constant is Rs into C, and the time period of the carrier signal is 1 by Fc, where Fc is the frequency of the carrier signal. The charging time constant should be short compared to the carrier signal time period, otherwise it will take more time to get charged or envelope of the input will not be created properly. So mathematically, RSC should be very less than 1 by Fc. When the capacitor is discharging, it discharges between the two positive peaks. This discharging of the capacitor causes a ripple in the output of the frequency Fc, and the discharging time constant is equal to R1C. Now, this discharging time constant should be long enough so that the capacitor discharges slowly through the load resistor R1 to reduce the ripple. But this discharging time constant should not be too long, as it will not allow capacitor voltage to discharge at the maximum rate of change of the envelope, or it simply cannot follow the envelope of the amplitude modulated signal. Therefore, for both of the conditions to be maintained, the discharging time constant or R1C must be very large compared to the carrier signal time period 1 by Fc, and very short compared to the 1 by maximum frequency of the modulating signal or FM. So mathematically, this condition can be summarized as 1 by Fc should be very less than R1C, which should be very less than 1 by FM. There will be some distortion in the output of the envelope demodulator. Let us understand what type of distortions can take place in the output of the envelope demodulator. Distortion in the envelope demodulator. There are basically two types of distortion that can occur in the envelope demodulator output, such as diagonal clipping and negative peak clipping. Diagonal clipping. In the selection of the RC time constant, we have said that this discharging time constant R1C should not be too long, because it will not allow the capacitor voltage to follow the envelope of the amplitude modulated signal. Let's consider a case where this discharging time constant R1C is very large. Then the distortion occurred in the output of the envelope demodulator is known as diagonal clipping. Due to this, the RC circuit cannot follow the fast changes in the modulating envelope because it clips the output from the original output. So the detector's output without the diagonal clipping looks like this, and actual detector's output with the diagonal clipping looks like this. Negative peak clipping. This type of modulation depends on the modulation index. When the modulation index K is greater than 1, then the modulation is over-modulation and the signal is said to be over-modulated. Distortion takes place due to the fact that the modulation index on the output side of detector is higher than the modulation index on the input side. Hence, At a higher depth of modulation of the transmitted signal, this overmodulation may take place at the output of the detector. When this happens, the negative peak will be clipped. Hence, instead of getting the output like this, we will have the output like this. That's all for this lecture. If you have any doubts regarding this lecture, then you may ask it in the comment section. And don't forget to hit the subscribe button. See you in the next one.